Lesson 4 is kind of a summary of everything. Don't try and write this down. You can get it later. Just kind of focus in. If we're in orbit, we can say gravity is what's pulling me in a circle. Then there are questions that ask how much work. If they ask how much work, it's going to be change in potential plus change in kinetic. Sometimes the change in kinetic will be 0. That's if you're just getting lifted up. Sometimes the change in kinetic will be, if you're in a stable orbit, there had to be a change in kinetic energy. We talked about escape velocity. Escape velocity was conservation of energy. You could tell that because the question didn't say how much work. So example 2 says, find the escape velocity. If you're escaping the planet, are you in a stable orbit? So please don't be telling me gravity is what's pulling me in a circle. Did it say how much work anywhere here? No. For escape velocity, what's happening? There's a change in height, a change in speed, and a yucky curvy force. Gravity is a curvy force. It's a job for conservation of energy. And we ended up with this really weird situation where for conservation of energy, your final energy was 0 because you were going to end up out at the edge of the universe. Potential energy was 0. And you were going to time it so perfectly that you were slowing down, slowing down, slowing down, slowing down, slowing down. Ding! You would come to a stop exactly when you got to the edge of the universe. I'll be talking a little bit more about escape velocity for the remainder of this lesson. Then we started looking a little bit at black holes. We found the gravitational field strength near a black hole. We found the escape velocity. Oh, it was big, 91.4. Yeah, it's a black hole. We found the escape velocity near a black hole. It was big. And then, using the escape velocity equation and letting escape velocity be the speed of light, we solved for R. We found the event horizon of a black hole. We finished off example 4. I said this was the longest question I'm going to ask you. How much work, change in potential, and you had to find change in kinetic, and you had to figure out your orbital speed. I said to you, I don't like this question. I will ask you a how much work question on your test, but I'll give you the orbital speed and save you a little bit of time. It's a lot of typing. We noticed a nice mathematical pattern. Example 6. Now, the good news is what I'd like to do is kind of look at every possible major situation I can ask you in example 6. It says this: a rocket at rest on the surface of the Earth blasts off from rest and rises to a maximum altitude height to a maximum distance big R. Write equations to calculate the work done by the engine. Assume the rocket begins and ends at rest. Okay. Brea, what's this want us to write equations to calculate? Work. Okay. Are we in a stable orbit? Look at the picture. If we were in a stable orbit, the rocket would be angled in this direction and going in a circle. Are we in a stable orbit? So don't be saying gravity is what's pulling me in a circle. What have they asked me to find? By the way, the reason I'm hyping this is what I've learned over the years is kids don't find the material that difficult. It's knowing which approach to use when that they find tricky. So what are they asking me to find? Work is the change in potential plus the change in kinetic. Wait a minute. It said assume the rocket begins and ends at what? So, gone. Now we've got the right start. Look up, don't write this next line down. Why can't I go mgh final minus mgh initial? Isn't that potential energy? Why can't I use that one? Little g is changing. As soon as we go cosmic, we're going far enough away that this 9.8 is going to change. So, I have to use the cosmic potential energy. Negative big G, big M, little m over R final minus negative big G, big M, little m over R initial. This is, I wrote here as a note, this is how much work it's required to lift something into space to get it to the right height. This will not keep it in a stable orbit. Why not? What else do you need to stay in a stable orbit? Kinetic energy, you need the right sideways speed, v orb, which I think was the square root of big G, big M over R. Well, gravity is what's pulling me in a circle, v orb. So, need KE. If we were rocket engineers, Zach, this would tell us how much rocket fuel we needed just to get it up there. Not to keep it up there, but that's step one. A rocket moving at speed v at liftoff near the Earth's surface rises to a height h with no engine use. So I guess they fire their rockets in a mighty burst to hit full speed instantly, and then they coast. We'll ignore air resistance. Write an equation to calculate the maximum height using conservation of energy. Assume the rocket ends at rest. George, what does this want me to write an equation for? Does it say the words, how much work? So don't be telling me work equals change in potential plus change in kinetic. Are we in a stable orbit? No. So don't be telling me gravity is what's pulling me in a circle. What's my approach going to be here? Help them out. What's my third option here? Conservation of energy. So I'm going to start out like this. KE initial plus PE initial equals KE final plus PE final. It says we end at rest, so I can do that. Oh, look up. Don't write this down. I'm starting on the Earth. Can I cross out initial? Where is zero potential energy if we go cosmic? Where did we define zero to be? Not on the Earth's surface. Where did we define zero to be? All the way out at? Now, if this question said something like, and the rocket ends up a very long distance away, or if it says an infinite distance away, then I could cross that bad boy. You know what? That's escape velocity, but we're not going to get there yet. For now, I guess, George, we would go a half mv initial squared plus negative big G, big M, little m over r initial equals negative big G, big M, little m over r final. What would be fair game for this specific situation? As far as I'm concerned, I could tell you the starting speed and ask you to find how high we get. Now, that's a little bit tricky because where is that on the... If I was asked to find RF, I would not get RF by itself. What I would do, Taryn, is I would calculate this whole thing as a number. And only then, once I had that as a single number, then I would say stuff moves diagonally, the R to the RF moves to the top, the number moves to the bottom, and then I would continue going. But this is where my love for getting things by themselves dies. Or I could tell you how far out we started and say, what's the impact velocity if it's an asteroid? Oh, if I did that, Zach, I could even have it have some initial kinetic energy. I could have it start with some energy. How would you get that V by itself? Same thing as I said before. I wouldn't. I would move this over, turn it into one big number, then I would get the V by itself. But I wouldn't try getting the V by itself now. Does M cancel here? Little m? Yeah. Does it cancel here? No. Which makes sense. It should take more rocket fuel to send the space shuttle up than a tiny satellite. But a tiny satellite and the space shuttle will both hit the ground at the same speed. A space shuttle will do more damage, but that's not what the question's asking. So I wrote here, if we know how much KE we start with, we can calculate maximum height. And in reverse, if I know my maximum height, I can tell you how fast I'm hitting the ground. A rocket moving at speed v at liftoff barely escapes Earth's gravity with no additional engine use. Write a conservation of energy equation that would allow us to solve for v. No, what do we call this? Do you remember? Something velocity. This is escape velocity. I went on my rant last day for those of you who were away. It should be called escape speed because we're using a scalar equation. We're not getting a vector answer, but they call it escape velocity, so I'll use the same term. So this is escape velocity. Danica, you were away. I'll pick on you to help you figure this out. What does it want me to use? How much work? No. Do you see the phrase, how much work? You have the notes in front of you too, right? You're following along, right? Did you want a copy? You said you printed them up. Did you want a copy? Okay. So, does it? What method does it say for escape velocity? What am I going to use? Okay. So you ready? Here's how we derive it for those of you that were away. Start out with conservation of energy. KE initial plus PE initial equals KE final plus PE final. We're going to escape the Earth's gravity. In fact, Danica, in the picture it says we're going to arrive out to where? What's our final potential energy then if we're all the way out at infinity as a number exactly? Yeah. Oh, and we're going to do this so perfect because as we leave the Earth, it is going to be slowing us down, slowing us down, slowing us down, slowing us down. Do you know when we're going to come to a stop? Out at infinity. So, you know what our final kinetic energy is going to be? Also zero. Now, this is a little strange because the whole right side is zero. Don't panic. I'll get this. A half mv initial squared plus negative big G, big M, little m over R final equals 0. Now what I would do, Danica, see this negative term? I would plus it to that side. And I end up with a half little m v initial, that's the escape velocity, squared equals positive big G, big M, little m over R final. Will the escape velocity for the space shuttle be the same as the escape velocity for a tiny little CubeSat? Do the little m's cancel? Yes. I'm going to get the V by itself. Xavier, how would I get the V by itself? And then this is escape velocity. V. You can add this if you really want to your blue sheet, but not to your yellow sheet. And I've showed you how to derive it. Comes out of conservation of energy. It's 2 big G, big M over R. And I wrote R final here. It should be R initial. I'm sorry. Right? Surface of the Earth. R initial. R initial. By the way, Xavier, look up. That's orbital speed. That's escape velocity. It's for us to get orbital speed, that takes most of our rocket fuel. To leave the planet once you're up there, not that much more required. A little more. Root 2 as much, so 1.41 as much. Okay. Odds are pretty good I will be asking you an escape velocity question in the future. And it's probably going to involve black holes because I dream, right? Next page, D. A rocket at rest on the Earth blasts off and enters a stable circular orbit of radius big R. How much work will the engines do? Assume the rocket begins at rest. Okay. Darman, what's this question want me to find? Change in potential plus change in kinetic, baby. Are any of these 0? Only the initial kinetic energy. So here, this is, in fact, I think I wrote, this question is a lot of work, but no, this is that one that's going to take about 12 lines. We'll find the change in potential very carefully. We'll make sure, did they give me a radius or an altitude? If they give me an altitude, I got to add the radius of the planet for the final. I'll backspace ditto marks and edit on my calculator. I'll get the change in potentials, like 5 sig figs, write that down. Then I start over with the change in kinetic. Oh, where did we say we're launching rockets from? North Pole, either Santa's Workshop or Superman's Fortress of Solitude. But that way our initial velocity will be 0. But otherwise, in real life, if you're designing a rocketry program, closer to the equator, the better. You take advantage of the Earth's rotation. That's free energy, baby. Use it. Totally. And make sure you use the cosmic potential energy here. I'm not going to break this one down further, except to remind you, Paige, what's changing anything? Final minus initial. Okay. Example E. A satellite moving at speed v at distance big R from the Earth's center falls to the Earth's surface. Ooh! Zach, what's this want me to find? Did it say how much work? Say no. So don't be writing work equals change in plus change in. If we're smashing into the Earth, are we in a stable orbit? So don't be telling me gravity is what's pulling me in a circle. So what would my approach be? Yeah. Can we use how much work? Did they say how much work?
No.
Then don't be telling me we can use work. Are we in a stable orbit? What's our third approach? If you haven't spotted, and don't feel bad, but what I'm saying is notice the pattern. We're really using three primary starting points. Gravity is what's pulling me in a circle if I'm in an orbit. How much work? What's the third one? Oh, is there a change in height? Is there going to be a change in speed? Is there a yucky curvy force because gravity is changing? Conservation of energy. So it's going to look like this. K E initial plus P E initial equals K E final plus P E final. And if I take this one step further, a half little m V initial squared. Now in this case, initial is outer space, not on the Earth. We're starting in outer space. Plus negative big G, big M, little m over big R initial. I'll use big R because that's what they used in the question. Equals a half little m V final squared. That's what they want us to find, V impact. Plus negative big G, big M, little m all over our final, which in this case would be 6.38 times 10 to the 6th the surface of the Earth. Are any of these zeros? Where would potential energy be zero? Where is cosmic potential energy zero? Out at infinity. If this question, Zach, had said the rock starts from a very, very long distance away, you could, okay, initial is potential is zero. It doesn't say that. In fact, it says it starts a distance r away. Nothing cancels as zeros here. I can say, hey, there's an m in everything. Okay. How would I get the v by itself? I would not. How would I get the r by itself? I wouldn't. How would I get this v? I wouldn't. How would I get this v? I wouldn't. I would instead get everything else to one side, turn it into a single number, crunch all the numbers, then I would get the thing by itself. And we'll do some examples like that. But I would consider this fair game as well. Okay? Do you see how we reasoned our way to the correct starting point? Doesn't say how much work. Don't be telling me work is changing plus changing. We're smashing into the Earth. We're not in a stable orbit. Change in height, change in speed, conservation of energy. Alrighty. Example 7. A satellite in orbit. Okay, the fact that I see that word, if I need to, I can say gravity is what's pulling me in a circle. Has a gravitational potential energy of negative 6.55 times 10 to the 10th joules. Oh, okay. Its orbital radius is 8.85 times 10 to the 6th. Is that a radius or an altitude? How do you know? You're right. Because it says orbital radius. So will I need to add 6.38 times 10 to the 6th to that? No. No. That's already, they did that for me. All right. Ooh. Kevin, what's A you want me to find? Okay. Don't write this down yet because I may start out wrong. I don't remember how to do this question. My first thought might be gravity is what's pulling me in a circle. And so I would probably do this maybe in my brain, but I'll write out, I would say, okay, big G, big M, little m over r squared equals m. And then I would say to myself, which version of A do they want me to use? The one with the V? Someone put their phone on vibrate, by the way. The one with the V or the one with the T in it? And I would kind of, in my mind, the noise that a record makes when its record needle scratches across, that noise would go because they didn't mention or ask for V. They didn't mention or ask for T. And so my brain would say, okay. You okay with that? That would be my first thought. Well, Kevin, what else did they give me? No, they did not. I don't see the word work anywhere. No, there's something else they gave me. You were on the right track, but you didn't use the words the way the question described it. Something, something, something. 3 words. No. Which doesn't say work. Don't call that work. What did they give me? Let's try writing out that. What's the equation for gravitational potential energy? The cosmic one. Negative big G, big M, little m over R. Apparently that equals negative 6.55 times 10 to the 10th. Can I get big M by itself here? Well, only if it's useful. Let's do a quick check. Do I know everything else? Kevin, do I know big G? Yeah, 6.67. Do I know little m? Do I know R? Oh! Okay, I thought this was going to be a lot tougher. Actually, I can find the mass of the planet just because I know how much energy is involved here. To get the big M by itself, I guess it's going to be times by R and divide by negative big G little m. The negatives will cancel. That's good. Mass is always positive. So it's going to be 6.55 times 10 to the 10th times 8.85 times 10 to the 6th divided by big G and 965. I know Earth is 5.98 times 10 to the 24th. I'm expecting probably something in the 10 to the 20s range because it's a planet. If I don't get that, I've made a typo. What do you get? This is worth practicing typing into your calculator. Oh, Mr. Decimal, Mr. Dewick. 6.55 times 10 to the 10th times 8.85 times 10 to the 6th divided by 6.67. Do you get, I guess, 9.01 times 10 to the 24th? Almost exactly, but not quite 9. Does that seem planet-sized? Yeah. Little larger than Earth, but not much. A little heavier than Earth. 9.01. I'm actually on the suspicion that I'm going to use this number. I noticed next to that 5, there's a 989. I'm going to write this as 9.006, and then I'll write it as 9.01. Mass is kilograms. Okay. Arsh, what does B want me to find? Suggestions. First of all, is it saying how much work? And don't go work equals change in plus. Okay. Suggestions. What else can we try? We just did that, maybe. What's the third thing that I can say? Because we're in orbit, what can I say? No. Does one of the versions of circular have a V in it? I know where I'm going. Okay, so orbit, gravity is what's pulling me in a circle. Big G, big M, little m over R squared. That one's not going to change. Equals little m. Which version of AC am I going to use? Darn right. Oh, you know what? This is V orb. We've done this. One of the R's cancels. We ended up with V orb. I almost have memorized this. Big G, big M over little r. Oh, which big M? The one we have on our calculator stored still. Which R? 8.85 times 10 to this. Okay. This will work. times 10 to the negative 11 times, answer button, divided by 8.85 times 10 to the 6th. That's way too, square root. It's like, that's crazy fast. Now, this isn't the Earth, but it's roughly the size of the Earth. For the Earth, I got orbital speeds in the thousands. The fact that I got one here in the thousands, do y'all get 8238.667 and that goes kind of weird? Yeah? Okay. I probably did this right, is my ballpark figure. I'm going to write 8,240. Did you get that okay? Are you lying? Okay. Type like the wind. Type. Good. 8,240 meters per, not squared, per second. Okay. Mason, what's part C you want me to find? That hasn't changed, half mv squared. So it's going to be 0.5. Which m am I going to use here? Little m, because that's the one that's moving, which was 965. Which v? The one that Arsh just found. In fact, Mason, I'm going to go answer button squared. And I get a kinetic energy of 3.275 times 10 to the 10th. I'm going to write all of that out for a reason. There's another way I could have done this. I don't know if a bunch of you were away Friday, but for those of you who were here on Friday, we noticed some patterns. The other thing I could have done was this. What was the potential energy in orbit? What did it say? They told me. What was it? Times 10 to the what? Times 10 to the 10th? I told you there is a pattern. Your kinetic energy in orbit is half of your potential energy, but positive. Is it? So if I was really lazy, or if I couldn't get part B, I can still get part C, even though I couldn't find orbital speed. Divide the potential energy up there by 2, make it positive. That's the kinetic energy. Ooh, what's D asking me to find, Kai? Total energy is going to be add the potential plus the kinetic. So if I add the potential, 6.55 times 10 to the, negative 6.55, Mr. Duke, times 10 to the 10th, plus 3.275 times 10 to the 10th. Hey, you know what? I get the same thing, because we also said the total energy is half of the potential, but negative. You can survive just fine without that, but Sarah, if you spot it, it's kind of, I probably did this right. There's no way we could have fluked into that if we didn't get the mass correct and the orbital speed correct. We must have. Had to have. My abbreviation for total energy is TE, I don't know. Negative 3.275 times 10 to the 10th joules. Now, for those of you that were away on Friday, that might have seemed very confusing. We did a little algebraic proof where we just noticed that pattern. You don't need to memorize it. You won't need it to answer a question, but it's kind of handy as a shortcut sometimes. Okay. So what's your homework? What did I assign last day? I said you could try number 1, 3, 5, 7, 8, 9 and 10 I had put a star next to because I hadn't quite talked about that. But now I've done the setup in all those examples that we looked at. So you can try that one. And then I said you could try 16, skip 17, 18, 19, and 20. Lots and lots of practice. Put your pencils down, look up.